Hey folks, how are you? This is Saddam Leonardo Kap and welcome to my channel. Today I'm going to talk about this newly launched AI by China, and its name is DeepSeek. As you have already heard so many videos, YouTube is flooded with the video of DeepSeek and how it has completely killed ChatGPT. So today in this video I'm going to talk about from the research perspective, right? So if you want to if your research is aligned with data science or cosmology or theoretical cosmology, you have already heard about this Hubble tension, that okay, whenever you try to measure this Hubble constant in the local universe, means that from the supernova analysis of Cepheid variables, it is coming out to be like 73 kilometer per second per megaparsec. On the other hand, if you try to measure it from the Planck data, that is indirect measurement from the early universe, the value of this zero is coming about 67 kilometer per second per megaparsec, and this is there is a discrepancy of 5 sigma level, right? So from the with this AI, newly advanced tech AI, I'm going to first understand that okay, what is the meaning of this Hubble tension, and what is the meaning of this SH0ES experiment, like what how we are actually measuring the L0 in the local universe and how it is operated in Planck Planck data, as well as we are going to ask this AI that all right, okay, I have this experiment, how one can resolve it, what is the way to actually think it. So in this video you are going to learn a lot of things, a lot of questions that is going to be answered by AI. Now these AIs are trained on the existing data sets. So if you will search the internet, there will be a lot of papers on this, lot of review papers. Therefore AI in this kind of thing, where you want to have a large literature review, where you have to do a large literature review, it is going to be very helpful for you if you want to start with this AI. Either you start with ChatGPT or DeepSeek research. Now I'm going to, in this video I'm going to particularly focus on DeepSeek because it has killed ChatGPT. So let's try to understand that how it is, very magnificent, and how its answer is going to be, very helpful if you want to delve deeper into these kind of research. So let's first start with, I have this question over here, that how does SH0ES experiment measure the Hubble parameter and why it is model independent analysis? As I told you that SH0ES experiment is based on the analysis of supernovae, and from the supernovae we are going to measure that our universe is expanding or not, what is the nature of dark energy. So in a sense we are directly measuring H0, and we are asking that why it is model independent, because in measuring H0 from this SH0ES experiments, we don't have to rely on any kind of models means that lambda CDM model, it has lambda CDM model means that it has many components. It has the dark energy component, is cosmological constant, and cold dark matter, as well as it has already assumed in its framework that the universe at the largest scale is homogeneous anisotropy, means that if you will average out, everything looks pretty much same. If you go to any angles, the universe would be appear very much same. So here in this experiment we are not going to do anything. So first of all, we have asked this DeepSeek that okay, how does SH0ES experiment measure the Hubble parameter, and it is model independent analysis. Yes. So now the answer it has given that okay. So first of all, why deep thing is very interesting. So if you have already seen so many videos, you have already understood that it is not fine tuned, right? It has trained with a lot of data, but it is working on the reinforcement learning, means that if you are producing an accurate result, it will be rewarded. So based on the reward and mechanism, it is generating the best possible answer for the users, and it has been trained in such a way. Supernova H0 for the equation of the state of dark energy collaboration is the leading project measuring the Hubble constant H0 using distance ladder approach. Yes. So if you want to, go deeper and deeper into the space, means that you are going very much in the past in the universe, past in the universe. So therefore, you have to use the distance ladder mechanism. It is often called model independent because it does not rely on assumption about the universe composition, e.g., dark matter, dark energy, or cosmological models like lambda CDM. So let's break down how it works and why it is considered model independent. Well, how SH0ES measures H0? The SH0ES team uses three rung distance ladder to measure H0. Right, three rung distance ladder. So first of all, rung one is geometric distance to Cepheid variable. Yes, Cepheid variables can be found in the Milky Way, and it has a very interesting relationship with its luminosity as well as the pulsating period. Cephid stars pulsate with period tightly correlated to their intrinsic brightness, that is called luminosity. The period luminosity relationship Levitt law allows them to act as standard candles. Method 1. Measure parallel distance to Cephids in a Milky Way via Gaia satellite data. Use these to calibrate the period luminosity relationship. So what you are basically inferring is that you can easily find out what is their pulsating period, and based on the pulsating period you are going to actually understand what is its luminosity, and based on the luminosity you can easily measure the distance. And how it can be done? So for an example, luminosity is proportional to period pulsating period to the power 0.7. From the parallax, absolute brightness m is known. So when we are measuring the distance to Cepheid variables, we know exactly what is the absolute brightness. And now here comes the problem that many scientists are debating, that when you are measuring these luminosity distances, there could be many errors. Many errors means that because of their environment is not static, their environment is dynamic, and a lot of stars are there that can produce a lot of discrepancy. And because of this, how can you say that whatever you are measuring, let's say that absolute brightness that is denoted by capital M is going to be, it's a very error free? There could be so many systematics involved which you have not taken into account, right? So apparent brightness. So therefore, another thing is that one thing is absolute brightness. Another thing is the apparent brightness, that is denoted by small m, gives the distance via m is equal to 5 log 10 d over 10. D is the distance from here to the Cepheid variables, and then plus of m, right? So now run to Cephids in nearby galaxies with type Ia supernova. So observe Cephid in galaxy that also host type Ia supernova. So whenever you are, if you are measuring in some kind of a galaxy, you have the measurement of Cephids. Now use that Cephid's luminosity, and you can use to reach another supernova. So that is why it is distance related. So suppose you have to, climb something, you use the base one, and then from the base you go higher and higher and higher, right? So based on the observation of Cephids, you go to the host supernova. So use the Cephid calibrated distance to determine the absolute brightness of SNEIA. So SNEIA type of a supernovae that has the brightness, and that brightness for any kind of supernova is going to be the same. So they have calibrated a distance using the Cepheid distance ladder, and they are actually measuring the supernova brightness. Now SNEIA, SNE1A then act as a secondary standard candles. So these are called very standard candles in our universe, and their intrinsic brightness is now known. So from this Cepheid calibrated distances, now I know what is the SNEI, what is the intrinsic brightness of supernovae, right? Because I know the distance. So now I know first of all, I know what is the luminosity of Cepheid. I know the distance, and in that particular distance we have a supernova. Now we know the distance, and with this distance I'm going to know what is the maximum brightness of, or maximum brightness or absolute brightness of the supernova. So this is the way we are actually calibrating the supernova, or know or understand the brightness of the supernova. That is too much important. Now measure H0 using distance SNEIA. Observe SNEIA in a galaxy at low redshift. Yes. So whenever you try to measure it, you are using some kind of particular redshift. Redshift is corresponding to the how much distance you are in the universe, or you are deep in the universe. So where the Hubble flow dominates, where the Hubble flow dominates, specular velocities are small. So as much as you go in the past, in the deep in the universe, the specular velocity is not to be very large. But as much you are coming very close to nearby universe, then you have then these objects are getting affected by specular velocities. As I told you, that it's because due to the neighboring kind of thing happens around it, right? So now use the Hubble law for the linear expansion. So you have this velocity, that okay, how these two things are, receding towards going away from each other. So like the velocity I can measure, velocity is proportional to h0 into d. So h0 is the constant. So this is basically the Hubble law. And here v is equal to c into z. This is called recessional velocity, where c is the speed of light and z is the redshift. And d is the luminosity distance from SNEIA. Hence, we can easily find out what is the h0. I know speed of light, that is redshift at which we are measuring, and there is d distance it is. So why it is? So this is the complete formula from which we exactly measuring that where our supernova is. Well, how we are measuring, how we can get the value of h0. Now, why it is model independent? The switch analysis avoids assumption about the universe geometry that it could be flat, open, or closed. We don't care about it. Dark energy and dark matter and no Friedman equation is required. Yeah. So, whenever we try to solve the Einstein equation, you require to first give it the shape of geometry. That, okay, what are the assumptions? And the very interesting assumption or very straightforward assumption is that consider universe to be homogeneous and isotropic. That is called Friedman-Lemaitre Robertson Walker metric. It's not required over here, right? Now, there is no early physics involved, right? So, early physics, whenever you want to understand early physics, you first require to have some kind of model, because these analyses are model dependent, not independent, right? So you have to understand model early universe, and whenever you try to understand this early universe, there are involving a lot of different things. For instance, there was first of all the radiation era, then there is a matter era, right? So universe first took birth, gone through the inflationary phase, which is a very accelerating phase. So at t is equal to 0, we don't know anything about it. Now t is equal to 10 to the minus 42 to the minus 36, near about, the universe has rapid expansion, that is called inflationary phase, and then radiation domination starts. And when we have radiation domination, it has a large temperature, and everything is kind of collapsing, and again there is a lot of gravitational collapse, and universe was expanding. And because of this collapsing and expansion, there is some kind of oscillation going on. And when the universe has expanded and no gravitational collapse was possible, then there is something called sound waves that can be analyzed in the universe, or it has kind of imprinted. So if you will observe those data, you see that okay, there is a sound horizon, sound wave horizon. So these things we can measure from early universe, but it has to be model dependent. It is sound waves in the primordial plasma or CMB based method. So CMB means that when the universe has now become the temperature becomes lower and universe becomes transparent, means that now the neutral atom has been formed. The photons can no longer knock out the electrons. So non-neutral hydrogen is atom has formed. So universe has, before universe was opaque, you cannot see anything in the universe, right? So now the electrons is bound with the hydrogen atom, and whatever the photons that you have there, it is not streaming freely. And these photons that we capture today is called cosmic microwave background. That is about 380,000 years after the Big Bang, right? So these photons we are capturing in the microwave region, and from there we can understand that what are the components of the universe, as well as we can understand that okay, there is some kind of fluctuation in the early universe, right? And this fluctuation means that they have some kind of inhomogeneity, and that's how we are inferring that in the early universe everything was homogeneous, but it's not completely homogeneous. There is certainly some kind of inhomogeneity would be there. Otherwise, we cannot observe the formation of galaxies, or we can have any kind of sensible universe if there is no inhomogeneity. Therefore, inhomogeneity must be there. But with this inhomogeneity, we must have this dark matter and dark energy. And when we try to mix a model and try to observe them, we found out that lambda CDM is doing very best with these kind of assumptions and so on. It is perfectly aligned with the data, but the values that we are getting on H0 is coming out to be a little bit problematic when we are comparing with the present time H0 data. So the key difference from CMB based H0s, SH0ES distance ladder measuring H0 directly using local universe, whereas in CMB infers H0 directly from early universe physics plus lambda CDM model. It's model dependent. Relies on empirical relationship, Cephids periods, luminosity, and SNEIA brightness. Relies on cosmological parameters like Omega m is basically corresponding to fractional energy densities of matter, dark energy, and the lambda CDM model. Now we have this low Z measurement. We say it's a local universe. We are not talking about very high redshift, like redshift is greater than 1100. Or over here in the CMB, it is basically high redshift, means that we have to use some extrapolation theory. Right. So here is the code that it is obviously have produced, that okay, if you just use some kind of dummy variable Z, and there is a distance from the SNIA, you can easily find out what is your H0. You can just fit the curve and you can easily find out the value of H0. So it's very interesting. So here H0 is 70 kilometer per second. So you can just replace with this with the data, and you can go and check out their papers, and you can find out the distances of SNEIA. Using those things, you can easily find out what is the H0 that you can obtain, right? Now the problem is that, what does it tell me about the Hubble tension? SUS currently finds H0 is near about 73 kilometer per second, 73 plus minus 1 kilometer per second per megaparsec, while Planck's analysis gives 67.4 plus minus 0.5. You see that error over here is half the error of this one, and because of this simple error, we have this discrepancy that is going to be very huge. I'm going to tell you about it, how we can find out this sigma values, this 5 to 6 sigma, because people can ask that, okay, how we can find it. So if you just do the calculation, simple calculation, you will find it, okay, this is 4, 6, 7 and 5, so this is 5.2, but you have to also, the difference is 5.2, but it is near about 5 to 6 sigma. So how is it possible? So you have to take, first of all, you have minus the central values, and then in the denominator you have to take a square root, and then you have to, whatever the error uncertainties are there, just a square and sum it. So 1 is square plus 0.25, so it is like 1.025, then a square, and it's near about 5 to 6 sigma. So this is how we can find out what is the discrepancy in the value. All right. What is the sigma difference? Now, strength and criticism. Strength, direct and empirical measurement, bypasses assumption about dark energy, dark matter. Criticism relies on calibration of distance ladder. Yes, we have to calibrate. Otherwise, if we are not calibrating, we are not able to measure the absolute brightness of supernova. And if we are not measuring the absolute brightness, we are not going to get anything out of it. Now, assume SNEIA a perfect standard candle. Some studies suggest evolution with redshift. Yes, there is a problem, because we cannot go near to the supernova and measure its absolute brightness. It cannot be done. So over here, whatever we understand, maybe we do not understand perfectly well the supernova analysis. So this is another kind of debate, is that, okay, are we even understanding the supernovae physics? So you can find out more about it. Now the question that I have asked is, why Planck data without SUS? You see that there are things like, if you have the supernova, when you have a lot of supernova, it is compiled in the Pantheon Plus, right? So the thing is that, before I'm going to do that, we want to understand that over here, how does SUS experiment measure Hubble parameter? Yes, I understand how the SUS parameter measuring it. The problem is that, okay, then why Planck data without SUS result? Why Planck data is just simply giving this H0 near about 7 kilometers per second? Because that is really important to understand. So now it gives me the answer that the Planck satellite measures the cosmic microwave background radiation, the afterglow of Big Bang, and infers the Hubble constant by fitting the data to a standard cosmological model. Right? The result H0 is 67 km per second per megaparsec from the interplay of early universe physics, geometry, and lambda CDM assumptions. There are a lot of freedoms to take place. So the parameters are very large. Now Planck's approach, the lambda CDM framework, the Planck collaboration uses lambda CDM model, which assumes that the universe is flat. The dark energy is a cosmological constant, and there is a cold dark matter that is dominating the matter budget. Matter budget, it is near about 27% or something like 30%. The CMB's tiny temperature measurement fluctuation encode information about the universe composition and geometry. Planck measures this fluctuation and solves the Hubble-Friedman equation to derive the cosmological parameters, including S0. Now, key physics, sound horizon, and angular scale. So these things are associated with the cosmic microwave background. The CMB power spectrum has peaks caused by baryonic acoustic oscillation that is called BOW. The sound waves in the primordial plasma that I explained you earlier. The sound horizon RS is the maximum distance these waves travel before the universe become neutral as a standard ruler. Yes. So when I told you that there is a gravitational collapsing happens, and due to when the matter has collapsed, it has gained a tremendous amount of pressure. It has outbursted. So now, whenever these two processes keep on happening, you have kind of oscillation, right? But when the universe has now completely expanded, or the expansion is larger than this kind of gravitational collapsing, then you have whatever it is there, it has just stopped, and this stop is now become kind of a standard order which is imprinted in the cosmic macro background. So Planck measures the angular scale of sound horizon, right? So what is, because if universe is homogeneous, then you can observe it in any way, so it's like a spherical kind of thing. Therefore we are saying that angular scale of sound horizon theta s in the CMB. Now the thing is that where you are, from where you are measuring, it's also depending on the point of view, right? The line of sight. So this is called theta s in the CMB. The physical scale of sound horizon RS, which depends on pre-recombination physics like baryon density, dark matter density, a lot of things. Like you have already heard about that Big Bang nucleosynthesis, right? Because we have to also account for deuterium and all the processes that happened in the early universe, right? Otherwise we cannot take into account. Therefore the mathematics, that is, if you want to make a model and try to measure these things, these parameters, that angular horizon, angular scale, or physical scale, that is RS, is going to be a little bit difficult. Now from this, Planck calculates the universe geometry and infers the H0 via H0 is equal to constraints from CMB over lambda CDM assumption. So why H0 is 67? The Planck values of 67, Planck values of H0 is near about 67, emerges from the three critical factors. One thing is matter density. The Planck's CMB data tightly constrain the total matter density about 0.315. It is nearly about 31%, 32%, right? So you may have already heard that, okay, why we are not considering, dark, radiation, because the component is very small, therefore we are not considering. Although you may say that, okay, we can tweak with the baryonic component or the maybe a radiation component, but you have uh, additional observations. As I told you, it is called Big Bang nucleosynthesis, where you want to understand what is the uh, what's what was the plasma doing, or the compositions like deuterium, heliums, and so on. And from there we can get the very good question on the baryonic density, uh, right? And with the radiation density, that is not going to be affected too much. Now over here, omega matter is containing the baryonic density, that is and also the cold dark matter. So that is, the whole proportional is 32%, about 32%. Now in Laplacidium, the expansion history depends on the balance between the matter, omega m, and dark energy. A higher omega m slows expansion, leading to lower value, right? So you see over here that in the Planck we are getting omega m near about 31%, 32%. Now flatness and dark energy. The flatness assumption that omega m, the total critical density, is equal to 1. So if you don't understand what is the mathematics behind it, you can see my other video and check out that, okay, what is the Friedman equation. I have given everything there, so you can understand better that, okay, why we have done this on omega m plus omega lambda is forces dark energy to be near about 69% to dominate today. So this is basically telling you about the energy content of the universe. Now the transition from matter dominant to dark energy dominant expansion is calibrated by the CMB, which prefers a slow early time growth, lowering H0. So what does it tell? The transition from matter dominated to dark energy dominated expansion is calibrated by the CMB, which prefers slow early time growth. So you see that it is actually telling you that omega m, you see that I cannot measure omega m, right? I have made the model. The model is going to fit with the data, and from the data we are going to understand what is this free matter, free parameter, what is the value of this free parameter, it is omega m, and it is coming out to be 0.315. So we have already made our model fit with the data. We are not predicting it. The data gives me the value. Now H0 is lower, omega m is near about 32%. It says me that you see that the matter percent is very huge. Therefore, we are going to get the lower 0. And that is a problematic when we try to measure it from the local universe measurement. Like supernova, we have the higher H0 near about the similar kind of omega m. Okay. So how we can push this H0 a little bit higher? You see that now it will come. There is a sound horizon again. Another parameter, the sound horizon RS, is determined by recombination physics like baryon photon ratio, that is called omega p, right? A larger RS would imply a smaller value because H0 is proportional to 1 by RS into theta s. So larger RS means that lower H0, because if the denominator is getting larger, H0 would be lesser. So Planck measures theta s and lambda CDM RS combine to favor H0 to be 67, and this is problematic. Now, model dependence versus SH0ES. Unlike SH0ES, which measures H0 directly using the local supernova, H0 is model dependent. So, if lambda CDM is incorrect, Planck H0 would change. So, what you can just do is you have the data, you can use your own model. Somehow, you can simply try to push this H0 a little bit higher by making this RS lower, and then you can adjust it. Then okay, so these adjustment cannot affect the local universe, but it is affecting the early universe, right? Because RS is coming from the early universe. So whatever the change you want to do in RS, it does not have to anything with this local universe. So we have to understand that how we can tweak those values, right? Because you may say that okay, if I just make a model that is going to have something related with the Planck data, then we have to do every analysis. No, you can always make these adjustment and say that okay, where your theory is making some kind of changes. And that's why a lot of people have proposed different models that is focusing on just only particular thing, and then they're comparing that okay, that if the theory is not leaving anything change in the local universe, then you can see the whole game and the tension can be elevated at some particular levels. Understood? So now we are going to understand those things bit by bit. Now over here there is a Hubble tension. So the discrepancy arises because of this Planck value. The tension suggests earlier the systematic errors in one or both. Yeah, obviously, because again we are doing the indirect and direct measurement. Systematic errors could be there. Now new physics, or maybe we have to observe, we have to do very good in the observation sector, right? But in the same time, we have to also understand that maybe it is the model that we are working with, right? Maybe we are assuming that our universe is just only dominating with dark matter and dark energy, and that is some kind of problematic. And new research shows there is a problem, there is a paper on the timescape model that shows that we don't require any dark energy model, right? There is no dark energy, and it is actually working very fine with the data set, right? So if it is compared with the data set and it is working very fine compared to lambda CDM model, not too much fine, but yeah. So they suggest that okay, there it could be some possibility that there would not be any dark energy, right? So it's a very interesting one. Now, how lambda CDM fixes H0? Assume the Planck measures theta s. This is the angular scale of the sound horizon is 1 degree, and calculate RS is 147 megaparsec for a flat universe. Therefore, H0 is equal to c over the speed of light over RS into theta s, and there is a f over here. That f encodes the dark energy and geometry effect. With Planck's omega and omega lambda, this gives you the H0 near over 67. So if you somehow parameterize this RS and try to elevate it, maybe you can get the result, right? So why other H0 probes matter? Independent method like gravitational lensing time delays bow often gives intermediate values like H0 is 70. So there is the different measurements, like we have the Planck measurement. Now another measurement is called the gravitational lensings, as well as the baryonic acoustic oscillation methods to actually measure the standard rulers. Now these will give you the value H0. So some is predicting 70, some is predicting 67, some is predicting 73. So there is a little bit discrepancy around this value. Now you may say that the value is not too much far, we can adjust it. You see that when we say there is a gravitational constant, that is a capital G, Newton's universal gravitational constant or the speed of light. These guys are not changing. They are constant, means they are constant. So if you are trying to measure it using any kind of measurement possible or observation possible, this value has to be the same. If it is not coming out to be same, the problem is there, right? Therefore, that is why we are actually putting our head and beating our head with the wall, that why it is actually doing this kind of things, right? So this is pretty much amazing, how this AI model is giving you everything, right? So if you want to start with the research, this is tremendously working fine, right? So here it is also giving us that, okay, you can go to the Planck 2018 result, or maybe check out the Valentino's paper on Hubble tension, and you will get a lot of interesting things. Okay, another question is that, why Pantheon Plus? There is another thing I told you, that there is a Pantheon Plus datasets. So if you will go to GitHub or just search Google, there you will know that, okay, there is a Pantheon Plus. And the SH0ES collaboration measures the measurement of H0 directly using the Cephids. So why Pantheon Plus without SH0ES? So if you just take a supernova, right, and you need some additional physics to actually calculate the brightness of these supernovas. So if you use, let's say, Planck data to understand what is the brightness of the supernova, then it is actually giving you 67, that H0 is 67 and the brightness is little bit higher. On the other hand, if you have this supernova directly measured using the Cephids, it will give you 73. So you have the same set of data of supernova. If I'm anchoring it to the Planck data, right, when I can get the H0, and from the H0 I will get the capital M, that is called the absolute brightness, the value is kind of higher. On the other hand, if I use the Cephids, where it is directly measuring the M, this M is kind of lower and H0 would become something like that, right? So that is why I have asked it, why Pantheon Plus without SH0ES giving H0 near about 67, and why SH0ES calibration is giving you 73. So if you will, that is the very interesting point. If you want to become a very good data analyst, you have to understand the data, how it is been taken, right? So here the explanation that, okay, the difference arises how the absolute brightness of type I supernova is calibrated, which directly impacts the inferred value of H0. Here is the breakdown. Yes, Pantheon Plus without SH0ES calibration. When the Pantheon Plus supernova dataset is analyzed without SH0ES calibration, it relies on alternative methods to anchor the absolute brightness of SNI that I explained to you, right? Now, these methods often tie into early universe physics or cosmological model, leading to H0 67 km per second. I told you that you have to use some kind of different model to anchor it in order to understand the absolute brightness of supernova. Now, key assumptions. Inverse distance ladder, it combines SNIA with baryonic acoustic oscillation or CMB data, right? So BAO or CMB provides the sound horizon as a standard ruler. The sound horizon is linked with early universe lambda CDM dependent. Hence, absolute magnitude of SNIA M derived indirectly from cosmological fit to CMB BAO, assuming lambda CDM. Example, if CMB constrain RS, that is sound horizon distance, the inferred M of SNIA adjusts to fit the data, resulting in lower H. Now you understood. So results of H0 is 67, emerging naturally from lambda CDM consistency with early universe. That's how you are getting. Still you are measuring the supernova. Alright. Now Pantheon Plus with SH0ES calibration. So when Pantheon Plus is calibrated using SH0ES, the absolute brightness of SNIA is determined empirically via distance ladder. I understood. Bypassing the lambda CDM assumption using Cephids variable. This leads H0 is 73 km per second. So it is just the thing is that I have this supernova. I am going to measure the absolute brightness. One way is that in your local universe, just go to the Cephids, calibrated it, and try to measure the brightness. Another way is that, okay, you have this supernova, I don't know H0, I don't know capital M. What you can just do is that, okay, I have this early physics experiments like the Planck. From there, I know H0, and I try to fit the absolute magnetic, absolute brightness, that is M. This coming out to be maybe lower or higher. That makes H0 near about 67, and it is actually producing the value of M. So this M and the M that you are getting indirectly is going to be different, and this is basically tensor. That these two physics are not aligned with each other, right? So key steps is the Cepheid. You already know what we have talked about. Calibration is there, and there is a Pantheon plus. So in the Pantheon plus, we know H0 is CZ over DL, D is the luminosity distance, and this is basically giving you H0 73 km per second megaparsec. And here you have this absolute magnitude of m minus m is equal to 5 log 10 dl 10 megaparsec, or just 1 10 parsec, or 1 megaparsec, and dl is, you can just use this kind of formula and find out that okay, m is brighter more. So if you see over here that if the m is getting more negative, so m is the value that is giving you minus 19.3 or 13. Yeah. So if your M is brighter or more negative, therefore the luminosity distance decreases. Means that when the things are appearing brighter, then we say that okay, the distance from here to that object is basically near, right? It's nearer, means that DL decreases. And when the DL decreases, here is the formula you have: DL is equal to CZ over H0. So DL has decreased, H0 is higher. So more the M, more negativity is, less the DL, higher the H0, right? So the tooth calibration is giving you M like minus 19.25 in magnitude. On the other hand, the CMB bow, it says that okay, no, the supernova that you are actually measuring is a little bit away from you. The fainter the absolute brightness is minus 19.35, and the little bit difference which is near about 0.1, this triggers the magnitude in the DL, the distance is 5%, and altering the H0 by 7%, which is 67 to 73. Now you understand the dynamics of these measurements, and that is very, very interesting, right? So this is the complete operation of this Hubble tension, that actually what you are doing over here and how it is affecting your measurements. So if you see any data paper, and you try to understand their measurements, you have to understand which physics they have used. Means that what are the parameters they are trying to fit, right? And if they are trying to fit something with any kind of tweaking, you will see kind of key difference. So if it would have been like minus 19.25, it would be 3, right? So it would be like 0.01, and this one would have decreased by like 2%, and there would be no kind of distance, right? So you see that this just 1%, 0.1 magnitude difference has giving us the tension, right? So that is why. So why this create tension? Because 2 plus Pantheon plus model independent and anchored to local universe. On the other hand, Pantheon plus CMB bow is anchored with the early universe. Therefore, the two methods disagrees. Why these two methods disagrees? Because of these systematic errors while calibrating the Cephids, or maybe CMB bow modeling, that okay, we are understanding whatever we have understanding about the universe, it might be wrong. There could be many components. There could not be many. There may be like no lambda cesium, right? There may be no dark energy, or maybe dark energy cannot be constant. Nobody knows what, right? There are some models that is floating around us that says that dark matter and dark energy could have some kind of interaction, because we don't know what is the nature of dark matter, because we haven't yet found it in our laboratories, in LSCs or different laboratories, where we're trying to understand, trying to have the probes, direct probes, but there is no signature of dark matter, right? So we have this cosmology, astrophysical cosmological signature, physics signature, but there is no way we have the direct measurement. Astrophysically, we have direct measurement, but it says that something is wrong. It could be systematic. It could be that there is new physics. Like one of the physics is coming out from the early dark energy, that is altering the RS. So that we call it, okay, if somehow you can just decrease the RS value, it increase the value of 0. So how we can decrease the sound horizon? It can be decreased if we use, there could be extra component of dark energy. So if we have extra component of dark energy, this oscillation would have already stopped before, right? So RS could be lesser. Or if you do not include any kind of extra component of dark energy for a very finite time, then you have RS is 147 kilometer. Like, okay, the expansion is not too much enough to have RS to be very small. So you are somehow producing this rapid expansion at that particular point. Again, it is very fine tuning, right? Because you are altering by your own, and you are saying that okay, there could be some kind of candidate, because I know where to fix it. So we are not throwing away lambda CDM. We say that okay, lambda CDM could be saved. This is how we are actually dealing with. Lambda CDM could be saved, but let us introduce another fine-tuned parameter. That's why early dark energy. That's why it cannot get Nobel Prize, no? Isn't it? So the thing is that it is a very good idea, but you are just saying that okay, there could be some kind of another fine-tuned parameter, and we have fine-tuned, and like this one, like just like we have this DeepSeek. DeepSeek is not fine-tuned, but on the other hand, ChatGPT, the O model, is extremely fine-tuned, right? So it is working in reinforcement data, that whatever is the best, it will be awarded, or if it is not best, it won't award it, and it is working very fine. So we have to also think in such a way that we have to do something to actually elevate this tension. If somehow we can altering RS, not just in the lambda CDM model, but maybe something different, right? So we have observational evidence. We understand implication for cosmology. The discrepancy highlights the Hubble tension and suggests that applying lambda CDM, yes, the revision of early universe sound horizon, unaccounted systematics in Cephids. So there could be, both the parties are over here guilty, right? We cannot just say that only one party is guilty. Maybe both the parties are correct. So how do you know? That is the very interesting thing. That's why we are, we are passing through the very interesting phase. Anyone is guilty. So we have to make our judges very good in order to actually capture who is a thief, right? So yeah. So that is the problem with everything. Now, what are the possible solution of Hubble tension? As I already stated what is the possible solution. The Hubble tension, the discrepancy in the measurement in early universe and so on, systematic errors in observation. Yes, the Cephid or supernova calibrated flaws issues relies on distance later approach. Potential systematic could be involved, like metallicity dependence of Cephid brightness, Gaia parallax errors of Milky Way Cephids, extinctions dust, or miscalibrated in host galaxies, right? So solution: independent calibration using the tip of red giant branch or Mira variables as an alternative standard candles. Yes, then what you can just do is that you can change the calibrated candles. Instead of Cephids or instead of supernova, go to this TRGB or Mira variables, right? Obviously with supernova, and use this TRGBs. Now CMB analysis biases. Issue Planck H0 assume lambda CDM and depends on sound horizon. Potential systematics could be unaccounted foregrounds, e.g. galactic dust in CMB polarization maps. Miss uh, Misestimation of optical depth tau to reionization. Solution: reanalyze CMB data with fewer model assumptions using ACT and SPT data. New physics beyond lambda CDM. Early universe modification. Maybe there is another kind of fine tune required. Maybe early dark energy, a transient dark energy component before recombination reduces RS, rising at 0 to 72 to 74 while keeping lambda CDM intact at late times. Challenging, requires fine tuning to avoid conflict with CMB polarization and Lyman alpha 4 forest data. Modified recombination, faster recombination means that the primordial magnetic field reduces RS, increasing at 0. So you have many kind of ideas that can reduce the RS. Or neutrino interaction, there could be many different interactions. Extra relativistic species where ineffective would be greater than 3.04. Now this value is near about 3. It is where somehow you can increase the relativistic species or self-interacting neutrinos after the radiation density, changing RS. So you have many ideas how we can change the RS. If you want to make a model, try to change your RS, either making too much lower Your model will be discarded, little bit adjustment to it, RS, and then you can find out that okay, this can push your H0 or not. Now, late time modification is also allowed. It is not just that early universe. Maybe there is some kind of late time happens, and there could be phantom dark energy of equation of the state. If you work with lambda, the equation of the state, that is the ratio of pressure to its energy density, is coming out to be -1. It says that it could be possible the dark energy that we are getting is not -1. The equation is -1. It could be lesser than -1, like -1.12. It should not be -20, -300. It should be like -1.12 or -1.05, and so on. Accelerate expansion more than lambda. Yes. Somehow, if you have that component, then it means that throughout the universe you have this larger expansion rate, right? Rising H0 at late times. So now issue conflict with supernova data unless omega evolves, right? In homogeneous universe, local underdensity mimics crystal local expansion. However, observation of galaxy flows disfavor this. On the other hand, there are some kind of ideas floating around that okay, our universe in the locality is kind of under density, right? Because everything has already far apart, so we have the region that is very underdense. So photons that is coming out appear to be very fast, right? That's why whatever the measurement that we are doing for the supernova is giving us a wrong result because of the underdensities. So hybrid model. The hybrid model is that late time transition, a sudden dark energy phase at Z is 0.1, reconcile local and global H0. So you can have this sudden transition of dark energy, right? Interact in dark matter and dark energy. You could have some kind of interaction going on throughout the expansion history, and maybe you can trigger the H0. Now, observational cross checks, independent H0 probes. So we have the gravitational lensing time delays measure H0 via time delays between lensed quasar images. Current value is near about 73, but the error is much more, right? So they are measuring the quasars. There is a baryonic acoustic oscillation plus Big Bang nucleosynthesis that is combining these two results and giving near about 69 to 70, avoiding the same sound horizon. So this is the way you can avoid the sound horizon if you have this baryonic acoustic oscillation measurement, right? Now, standard silence. Use the gravitational waves. So gravitational waves are called standard silence, and you have already heard that. There is people have already got some constraint because when there is a gravitational merger happen, and again then there is a neutron stars. So not only black hole can merge, neutron stars can also merge, and neutron star is also emitting some light. So when they merge, they produce the gravitational waves ripples. At the same time, they are also producing the light. So if you try to measure them, you can constrain the speed of gravitational waves, right? And because of these constraints, you can easily find out what is the H0, and this H0 is coming out to be 70. But the systematic errors is very huge, so we cannot just rely on this one. But it's also becoming a very great, you know, uh, amazing, amazing candidate to measure the H0. What is the value of H0, right? So there could be there could be no tension, right? That whatever the value that we are measuring from the Cephids, maybe it is calibrated wrong. But why we are calibrating wrong? So obviously it requires some kind of physics, right? Now, theoretical reinterpretation, revisiting the sound horizon. So, sound horizon has again the model, and you see that what is the so if RS is smaller than lambda CDM predicts due to EDE, Planck H0 would rise, and therefore you got this 5% increment. So we can reduce it. Therefore, non-flat universe, a closed universe slightly rises H0, but Planck disfavors it because Planck favors that the universe is at the largest level is actually flat, right? So maybe if you do the closed universe analysis in the local, you see that omega k non-zero is allowed, right? And omega k is negative allowed, but including the Planck data, it doesn't allow, right? So machine learning approach, obviously machine learning, you can do the machine learning. That is what we are doing. Basically, I'm trying to learn the machine learning approach. Right. So improve distance ladder calibration, analyze CMB maps, likelihood free parameters, and so on. Current state of sensors is no single solution is universally accepted, right? And the key papers over here, it's there, right? Now you can say that could you tell me more about RS, the sound horizon, and what is it? What is the mathematical expression for it? Because if if we're talking about RS, then it's not too much clear. Okay, what is RS? What is the mathematical expression? You see that RS RS is the fundamental scale in cosmology that arises from the propagation of sound waves in primordial plasma of early universe. It serves as a standard ruler to measure cosmic distances and play a central role in both cosmic microwave background and baryonic acoustic oscillation. Below is detailed breakdown. What is sound horizon? Definition: the sound horizon is maximum distance that sound waves could travel in the photon baryon plasma before the universe became neutral, like 1100. Now, key events: pre-recombination. Photons and baryons are tightly coupled, forming a fluid that supports sound waves, baryonic acoustic oscillation. Recombination. Photons decouple from baryons, freezing the sound waves. Drag epoch. Baryons are released from photon, drag slightly after recombination. Yes, because universe is expanding. Therefore, whatever the R is, it would be a little bit dragging. Therefore, ZD, when it is dragged, it means that it is very near to us. Therefore, ZD, whatever ZD you are measuring, it has not decreased from 1100 to 1060. I'm marking the freeze out of the bow pattern. So mathematical expression RS is basically you have to 0 to TD or 0 to ZD, CS of T over A of T. Now you can, uh, change the variables, write everything in terms of this scale factor is A, dt is equal to dA over AHA, and the RS is written in terms of A, or maybe you can write it in terms of directly Z, because whatever data you have available is written in the Z, or maybe you can, change it. Now you have the sound speed, and the sound speed, because CS is not this, not the sound speed, not the light speed, right? CS is the sound speed. So CS is related with the geometry or the component of the universe via this one, that is speed of light over square root of root 3 1 plus RA, and RA is the ratio of baryonic density to the photon density. So if you know these densities, you can easily find out what is CSA based on the model, because now you have HA also. So HA is coming from the model that you have assumed that, okay, how the universe may look like. So maybe you are working with modified gravity. Assumption is again FLRW, working with FR gravity, any kind of gravity, FP gravity, FU gravity. So you know what is HA, you know what is CS, you just use this one, right? If you know what is the omega b omega gamma, right? Omega gamma is just the radiation density or photon density. You can easily find out what is your RS, right? So Hubble parameter is again, if you have the lambda CDM, this is the way you can write the parameter. Omega is going to be very small, that is 10 to minus 5, right? And now there is a drag epoch, that is AD, or the redshift ZD is AD over 1 plus ZD when baryon decouples from photon approximately by fitting the formulas on omega p h square. So these densities you can easily infer. Now you have the key dependency, obviously, in order to find the RS. That's why you say that, you cannot just simply say that, okay, RS could be anything. There are a lot of things going on, because over here, you have this RS, and this RS is depending on the densities, a lot of different densities and so on and so forth. So therefore, and also a lot of constants are all involved, right? Like speed of light and so on. So there are many models that is also assuming that, okay, we are not varying this omega b and omega lambda. So why not we are varying this constant? Maybe speed of light is not the speed of light we are measuring. Maybe throughout the universe it could be changed. Well, the constant could be changed, right? So there are models that can account these kind of changes, right? Now over here we have this observation model. So CMB acoustic peak. So if you will see the CMB graphs, there could be, there are many peaks are there, and these peaks are giving you the angular scale of the first CMB peaks. Theta s is steer to RS. The co-moving angular diameter, that is dm, is related with theta s is equal to RS over dm. This dm is too much important, right? And Z star is the period of recombination, that is 1100, and measures the theta. So theta is the calculation of theta is again the most important part, because it is related with the caustic peaks. A smaller RS would require the smaller dm. Smaller RS means that smaller dm. The larger H0 to maintain the theta, because theta is not going to be changed. Whatever the angular peak you are seeing, it is going to be there. So now you have these two free parameters, and they are entangled with these, entangled in the fraction, right? So if I make this theta has to be small or constant, these has to be, if RS is getting bigger, dm also becomes bigger. Now RS has to be small, so dm has to be also small. Now you have bow in galaxy survey. So if you just use the galaxy survey, galaxy data, you will encounter this bow imprints a characteristic scale RS in the galaxy distribution too. because you see that photons and baryon, they have decoupled, and they had this uh, oscillation going on. So these oscillations have imprinted in the galaxies, right? Because they have produced the inhomogeneity, and because of them, we are seeing whatever the structure is present today. So measuring bow in low jet surveys, like, because in galaxy formation we cannot find galaxies in the very higher redshift, in the lower redshift. So there are a lot of surveys like Bose and DC survey provide a standard ruler to the constraint, that is dV, volumetric distance, proportional to RS over H0 to the power 1 by. So if you use the bow data, that is again the late time data, so you no longer anchor your supernova with the CMB, but you see that again bow is also giving you a 0 near about 70, isn't it? So it is a little bit higher than the Planck, but it is not very close to the SH0ES. So connection to Hubble tension, early universe, late time solutions, early dark energy, or maybe modify recombinations, alter the CS or HA to sync RS. The example calculation could be over here. Whatever the class, there is some kind of class code is there. So you see there are a lot of things over here by you. Now how you can do it, you can do it just by reviewing some kind of paper, and you have also numerical code present, because if you want to analyze the CMB data or maybe some power data, you require this inhomogeneities to take into account in a model. So first of all, you have to define a model in the background, then you can introduce the inhomogeneity in the metric. Consequently, you have inhomogeneity or perturbation in the meta sector, and based on this, you are going to calculate the density perturbations, and you have to solve the Bode's manipulation. And it can be done using numerical codes. Numerical codes like class and CMB, class and CAM, and this class and CAM you can visit. You can learn these codes through this deep learning or deep think, right? Or DeepSeek or ChatGPT. These are complicated, not too much complicated. Not too much, not. It is actually complicated. I'm going to make some tutorial video how you can calculate with these, how you can use this code and fit your model. But again, it's going to take some time, right? And there is another thing I have asked. In some cases, people use two different standard rulers. One is called RS and another is called RD. RD is, now you have understood it. RS is the sound horizon and is the epoch horizon. I want to know the detailed difference between them, and in the data analysis, where should I use it, right? So over here, yesterday the server was busy. The distinction between RS and RD is subtle but critical in cosmology. Both are related to sound horizon, the distance wave travel in the early universe plasma, but they are correspond to slightly different epochs or use distinct observational context. Let's break them down. Because why I have written RS and RD, because if you see the paper of Planck 2018, they have used these two rulers, RS and RD. So you may understand, okay, what is this one, but basically they are the same thing. I told you they are direct. So RT is sound horizon and drag epoch. Drag epoch, the time when baryons decouple from photons after recombination, baryons stop being dragged by photons and begin to cluster under the gravity. So definition is again the 0 to TD CS over this one. So where TD is the time, again you can change it into a Z, and C as the sound speed in the photon baryon plasma, and A of T is the scale factor. So key role sets the scale of yeah, bow in galaxy surveys. So bow is a standard ruler corresponding to RD, right? Now RS, sound horizon and recombination. So over here, what is sound horizon and drag epoch? You have to understand what is the key difference. So it is usually used in the baryonic acoustic oscillation data. Now RS is recombination epoch at Z star is 1100. Over here it could be Z is 1060. The time when photons and electrons combine to form neutral hydrogen, making the universe transparent, it's freeze out. That is the definition. RS is 0 to T star CS over 80. The key role is that CMB acoustic peaks theta S is RS over D. So if you are trying to measure the information from the CMB peaks, you have to use this one. Theta S is RS over D. And so these two scales are kind of different, although they are same. So expect RD, RS. So it is there. Drag epoch, that is the recombination epoch, right? Physical process. Baryon stops being dragged by photons. Photons decouple from baryons. Now, bow and galaxy surveys CMB acoustic peaks slightly smaller, 147, near about 147, slightly larger, 148. Dependence more sensitive to omega BH and more sensitive to omega H. So from the Planck, if you're measuring the RS, and this is more sensitive to omega m. In the RD, it is more sensitive to baryon density. So why two definitions CMB versus BAO? The CMB sees the sound horizon at recombination RS when photons last scattered. BAO in galaxy sees the sound horizon at drag epoch when baryon began clustering. The two epochs are separated by 40 million years, leading to a small difference in RS and RD. Numerical examples like RD is 147, RS is 148. The difference is near about 0.7, although it's small, but matters for precise cosmology. So when to use RD and RS in data analysis, bow measurement, galaxy surveys like BOSS, BASIC measure the bow scale as RD, where dV is the volumetric average distance. Combine bow plus CMB when using bow to construct cosmology, always pair it with drag epoch horizon RD predicted by theory, right? RD in physics. If testing models that alter the baryon photon coupling, use RD. Use RS. CMB analysis. The angular scale of CMB again peaks depending on RS. Parameter inference when lifting lambda c when fitting lambda CDM model to CMB data. RS is the relevant quantity. Late time universe probes if combining CMB with H0 ensure consistency in RS. Common mistakes to avoid: mixing RD and RS. Do not mix it. Using RS instead of RD in BAO analysis introduces a small but systematic bias. Example, if BAO paper quotes DM RT fiducial over RD ensures your theory predicted using RD, not RS. Yes. Assuming RD is RS, while RD approximately RS in lambda CDM, this approximation fails in model like early dark energy, where RD and RS diverges. Yes. Inconsistency cosmological code. Tools like class and cam compute both RD and RS. Double check which one your code out. Whenever you write code, I will also, I have also made the code in BAO. I have used the RD, not RS. So if you incorporate those code is the Planck data, then you have to ensure that you have to keep this RD and RS out of the picture. Now, example, combining CMB and BAO data. Suppose you're analyzing CMB and DESI BAO, uses RG 148.1 megaparsec, computes theta s. BAO use RT 147 megaparsec to compute dV over this, right? Consistency check. In lambda CDM, the ratio of RT over RS is 0.995. If your model predicts a different ratio, it may indicate new physics. So this is also a very interesting thing, that RT over RS must be in between 0.995, right? Now, impact on Hubble Tension. Models like early dark energy reduces both RD and RS, allowing a higher H0, keeping theta s consistent. However, ED reduces RD more than RS, breaking the lambda CDM consistency between BAO and CMB. This is the key test for such models. So you see that if you want to know more about this one, so I hope I have given you everything related to Hubble tension and the data analysis perspective, why something is important and when something is kind of, you can change it. So which parameter to be play with and which parameter to be left, and how we can make a model that just only focusing on or triggering those points. And whenever you read those data analysis paper, you have to understand that what they have used and what they are actually talking about. Why, when you're using that, okay, this is the SH0ES calibrator, what does it even mean? And when we are combining the data, like let's say when we are combining the Pantone plus SH0ES, then why it is giving you some other values and so on. So these are important. So in the future, I'm going to make more videos on these ones. So you see that that is how you can use these today's AI in order to understand, in order to accelerate your understanding about the research, so that you can come and do a lot of things, because this AI model is not going to give you the new ideas, but they are going to give you the tool to analyze those things. You don't require any kind of professors to do it, right? You can just use these ones to actually giving you a better understanding, okay, how what is happening and so on, because they are going to they have already analyzed a lot of research papers and so on, right? So if either you can just go and read the research paper, or you can just start with these things and then read the research paper, and you will get the complete insight. So I hope you enjoy this video, and you can watch my other videos where I have given the codes, and a lot of fun is there. So this is the Leonardo Kap signing on.